I guess I might be the only professor today who's actually presenting. We usually call it teaching in this forum. So maybe because of that, they gave me a little bit more time, or maybe they always think professors like to talk a lot. They give me a little bit more time. But I'll do my best to give you an interesting overview. Typically, it is expected that professor shows a lot of equations and things like that. I'm not going to do that. I might use one or two equations here and there, but my intent is to really more give you an overview of some of the developments, in particular in the arena of electromagnetics, with focus on antennas and the role that antenna plays in general in this endeavor. So for you to know which one I am, I'm the one that with the arrow in the picture, and we're going to see the rest of the presenters, of course, as time goes on. And also, I look at the abstract of many of the presenters. I've come to conclusion that a bunch of things I'm going to talk about, they are going to enhance and actually enhance them from the industry viewpoint. So hopefully it should be a good complementary presentation for you. I greet you from UCLA. I welcome you to come and visit us whenever you are in the Southern California. We have a nice campus, and hopefully you'll enjoy visiting us if you haven't done yet. So what I'm going to talk about, I have entitled this From Maxwell's Equations to Modern Electromagnetic and Communication Antenna Engineering Marvels. As was said, Yair Ramatsami, professor at Department of Electrical Engineering at UCLA. So the presentation would bring us from Maxwell and evolve us to some of the interesting application of the Maxwell's theory into the realm of the industry and communication application in particular. So let me tell you where I'm coming from. For those who are interested in space, I'll bring you from a solar system to Earth and Southern California and ultimately Los Angeles and the Westwood campus. So we are very nicely positioned in Los Angeles for some of you who haven't been there. So again, we'll excite you to come and visit us. And we always guarantee some good level of sunshine. And I was really very pleased yesterday when I arrived here. I thought maybe I'm in the wrong city. It was a beautiful day, no rain. Well, congratulations to organizers who were able to arrange that beautiful sunshine yesterday. Now, if you look at our department is compartmented in several different areas: circuits and embedded systems. Then we have physical and wave electronics, and we have a signal and systems. So these are all complementary disciplines, which allows us to cover all kinds of areas, hopefully related to the communications and beyond. Today, I'm going to focus primarily on the electromagnetic antenna part, and that hopefully should give us a vision of what this talk is all about. Of course, we are into the interdisciplinary world. So these are the emerging opportunity in the interdisciplinary areas like photonics, electromagnetics, MEMS, nano, and solid states and plasma electronics. And we collaboratively work with other professors to get engaged in all these areas in collaborative fashion. And the frequency goes from low frequency to terahertz and beyond optics, of course, when you talk about the photonics. Now, I strongly believe that university must be considered as vital players in creating new and visionary concepts for future communication systems. This is a kind of a roadmap of my lab and some of the activities which I'm going to talk about a little bit more today. In particular, I'd like to amplify UCLA Antenna Laboratory in cooperation with other institutions is advancing novel antenna design concepts and developments for modern communication application, and that's where the focus of my talk is about. Now, I would like to bring a profound statement by Einstein, which I think it will roadmap my presentation a lot more effectively. We, of course, should cherish, as this forum is all about, to think about out-of-the-box concepts. The first speaker related to this very nicely about the future of networkings and IMS and so forth. Now, the statement that I'm going to bring to your attention is like this. It's by Einstein. He says, if at first an idea does not sound absurd, then there is no hope for it. I think it's a very profound statement. For researchers, this is the heart of what we do. If at first an idea does not sound absurd, then there is no hope for it. So I'm going to dive into this as a starting point and see how some of these absurd ideas have come to fruitions and application. So an absurd idea almost 20 years ago was the following. One of the most inspiring dreams of mankind has been to create global connectivity anywhere, anytime, with anyone, with any amount of information. Of course, in order this idea to come to fruition, first we needed to create the EM waves. Unfortunately, nature did it for us. And it was finally formulated through Maxwell's equation, the creator of electromagnetic theory, and this is one of the two equations I show in this presentation, which allowed us to appreciate the nature of electromagnetics, because before understanding electromagnetics, none of these stories could come to the fruition, clearly not. So when I teach this Maxwell's equation to my students, I only don't show the equations. I want to go to the heart of this equation. This equation conveys a lot of information, which I have labeled here. Tremendous amount of knowledge is hidden in this 4 equation. And by unraveling this hidden knowledge of this equation, we come to so much industry utilization and application of the concept. Now, of course, Maxwell didn't live too long. He only lived about 48 years old. But that span of time, this creation was ultimately one of the most profound kind of evolution of science and ultimately into engineering. So we believe strongly that these 4 equations forever change how we live, play, and enjoy life. And that's what all this discussion of this forum is all about. Now, Maxwell birthplace is Edinburgh. If you get a chance to Edinburgh, Scotland, you can go and visit. And there's a very nice museum about Maxwell's work. It's not only electromagnetics. He did a lot of interesting things about lights and other scientific endeavors, in particular also some Maxwellian distribution and so forth and so on. I had the opportunity to take a picture, so if you go there, make sure you stay by Maxwell portrait. This is his famous portrait, so I had to take this picture. I'm teaching Maxwell's equation for so many years, I had to have this picture with his original portrait there. Now, what came out of the Maxwell's equation were 2 profound concepts. That is, an amazing consequence of Maxwell's equation was time-varying currents radiate electromagnetic waves. And that's when you pause about this consequence, is amazing. I've been teaching this whole story for many, many years. Still, whenever I think about this, I get goosebumps. Why does the nature do that? Why does the nature does this in particular? That is, if I have a time-varying current, it radiates. We are going to expand upon that. And that's the heart of a discussion that we have today. And what is the role of antennas in particular in order to control this radiation that ultimately allows us to do communications? That was the first consequence directly from mathematics of Maxwell's equation. The second consequence was that how fast does electromagnetic wave travel? If some of you have your Ferrari here, you can go probably 200 miles an hour if you don't get a ticket. When you go on the plane, you can go 600 miles an hour. And then when I talk, my sound waves goes about 720 miles an hour. But when we look at the speed of electromagnetic waves, it's amazing. And that is 666 million miles an hour. That's an amazing number. This is extremely fast. And from the theory of work by Einstein, nothing can go faster. So we are very fascinated. We are working in a discipline that nature has created the ultimate velocity for its propagation or for its going from one point to another point. So it's great that we are in this business. And that is exactly our business, to create a communication using the vehicle of the fastest things that can happen in the nature, and that's great. Then, of course, this is the beginning of my talk, a little bit of history before I go into more depth of the antenna activities. Then, of course, it took Mr. Hertz to actually show that it can be created. And if you go to the Munich Science Museum, you can see his apparatus that believed to be first controlled radiation through the sparks and its collection by this loop antenna here. So for the first time, Hertz demonstrated the production of EM waves. Even Maxwell worked so hard, theoretically developed them, but he never experimentally demonstrated that, but Hertz was able to do that. Then it took the genius of people, in particular Marconi, to say, wow, if I can send my electromagnetic waves with such a speed, why can't I use that to convey some information if possible? And that was the dawn of the wireless communication. For the first time, Marconi showed commercial viability of the wireless communication in 1895. So then we needed second things to be done. Maxwell's equation was the first piece of the puzzle to reach us to our dreams of the big dream of mankind, connectivity, any place, anytime, and so forth. The next important puzzle was discovered by Shannon. And that's the concept of sampling, because that sampling now allowed us to bring all these digitization and so forth. Sorry about this, something went wrong with the computation. I brought it on this computer. It looked fine on my computer. The most important thing came of this Shannon was band-limited signals can be reconstructed from discrete sets of data sampled at specific sample points, and that revolutionized. In other words, if I have a signal which is in frequency is band-limited, I don't know to have that signal at every point. I only need to knowledge of the signal at some specific point, and that changed our whole life, how to do communication, all the codings, and so forth and so on. So these two prime manifestation of mathematical understanding of the laws of nature, in particular Maxwell's and Shannon, allowed us to come to this age of communication. So then it took scientists, engineers nearly 150 years to fulfill this dream of mankind. So whenever I teach my course, I tell the people, your cell phone is an engineering marvel with tremendous complexity. Then I amplify upon them. Next time you use your cell phone, please look at it with a great sense of gratitude directed towards so many pioneers who made this engineering marvels a reality. Nowadays, you see kids and myself and other places, we put your cell phone, we put it under the table, we throw it here, we throw it that. I amplify, please look at it and spend 2 minutes and look at it more carefully and just believe that how many people were behind this technology to happen. And this forum, of course, is a manifest of hopefully this gratitude to these people, pioneers who put this whole technology together. Now, recently there was a proceedings of IEEE just came out in July, and it was entitled Antennas in Wireless Communications. If you look at the front page of this proceedings of IEEE, it says, this cover page meant to suggest our growing dependence on wireless communication and the importance that antenna technology plays in keeping us connected. And that's where we're going to talk about the importance of antenna to keep us connected, and this proceedings of IEEE is a good reference to that. Now, if you walk through these proceedings, you see several topics, and I touch upon some of them here and there. One are the basic techniques. We have very much advanced how to play or work with Maxwell's equation. And that has brought us the advanced computational techniques, like method of moments, finite difference time domain, finite element method, geometrical theory of diffraction, and hybridization of these techniques. That allows us on the computer to do very detailed design. Along with that, we also have evolved, and I'll talk about this, advanced nature-inspired optimization techniques like genetic algorithm, particle swarm optimization, and so on. And finally, in order to complete this whole passage of basic techniques, there are also modern measurements, and there are many vendors in this conference who also display their work. This could be far-field measurement, near-field measurement, compact ranges, reverberation chambers, and etc. Of course, the time is limited for me to go all of them, but I give you some overview here and there. The next important items as we grow in this talk is innovative wireless antenna designs. And there are many components on them. That is, it could be printed slot and wire antennas, novel patch antennas, dielectric resonators, leaky wave antennas. Then you go to millimeter wave and terahertz antennas, smart antennas, reconfigurable antennas, antennas for software-defined and cognitive radios, and ultimately, more recently, metamaterial-based antennas. I touch upon some of them. Of course, if I grow in my business, in my research, I'm planning to also design a new class of antenna. I want to call them genius antenna. It's beyond smart, but we'll see how it goes. And ultimately, of course, we had to link that to modern applications. Modern applications, of course, cellular phones for mobile communication, 1G, 2G, 3G, 4G LTEs, wideband antenna for base station, ultra-wideband antennas for communication system, antenna for Wi-Fi connectivity, antennas for UHF RFID tags, antennas for mobile digital TVs, antenna for global navigation satellite systems, and antennas for medical and body-centric wireless communication. Again, these are the areas that a lot of research activity is going on, and I'll try to show some samples here and there. So if you look at this in a bigger picture, this is the paradigm wireless communication, and the importance and paramount components of this development are indeed the antennas that we are going to talk about a little bit more. Design, modeling, for various applications, human exposure, they're all components on that. And we believe now we can optimize antennas for almost any needs. So if you are interested, try to contact us, we might be able to help. So how does an antenna now radiate? Now let's go back to some fundamental physics here. And these fundamental stories are very important to get a good feeling about it. Fact from physics, accelerated charges radiate. If you take this to your heart, accelerated charges radiate. That is the paramount physics of what is going on. I don't know why the nature does this, but we as a human race are able to comprehend it. And once you comprehend it, then you can apply it to application. So if you look at the current is the charge time velocity. If you differentiate that with respect to time, that's the derivative of velocity, which is acceleration. So immediately you make a very profound observation, namely, time-varying currents produce electromagnetic waves governed by Maxwell's equation. And that's so important. Time-varying. So anytime you have time-varying current, it creates electromagnetic waves, and that's where we see all these problems potential with interference and all that, because it creates electromagnetic waves. The frequency depends on the rate of oscillations and so forth and so on. So how will you define an antenna? This is my presentation of definition. Antennas are electromagnetic devices controlling the flow of the time-varying current, thus producing EM radiation with desired characteristic. That's the role we play, how to control that radiation for putting a nulling in this direction, having a highest directivity in that direction, and so forth and so on. And these are some examples of antennas that we have working. It could be a fractal antennas. It can be very large space antenna to hopefully in the future map the black holes. It could be a cell phone antenna arrays and so forth. I served as a department chair from 2000 to 2005. And at one occasion, they invited me to go to a Beverly Hills Rotary Club. I don't know why they did that. And they wanted me to talk about what I do. So how would you explain your work to people who are in industry like banking, lawyers, and other kind of activities that they don't have any relationship to what kind of work we do? So I had to come with some ideas how to present it and get them engaged that what I'm doing might be of interest to them. So I came with this idea. I said, like Van Gogh, who used his brushes to create paintings, electromagnetic scientists are artists who are able to paint the radiation of electromagnetic waves with their antennas. So I gave them an analogy. Antenna is like a brush. We paint electromagnetic waves. Other people like Van Gogh who cut his ears, I haven't done that yet. So he uses his brushes on the canvas. So I challenged them. These are his paintings, and these are the paintings that I have generated in my work. And I told them I believe my paintings are more beautiful. But of course, I got challenged because they said Van Gogh's paintings are sold, some of them for $35 million. My paintings maybe $5 or something like that. But hopefully we can do better. So what is the question? The challenge is how to design and optimize antennas. So we are going to say a few words about that. So from the viewpoint, what this antenna does, antenna really fundamentally are the matching devices between gadgets, whatever to the front end, to the backbone of the, say, electronics or whatever, and the space waves. That's really the role antenna wants to play. This is a very important point to be appreciated. You work so hard to generate electromagnetic power through your generators and so forth. You guide them through some transmission line or waveguides, but ultimately you wanted this energy effectively to radiate. That's all you care. Because if I want to communicate from here to Jupiter, or I want to communicate from here to another part of the city in Seattle, I want to have most of my energy that I have spent money to create goes through my electromagnetic waves. And that's the role that the correct antenna does play. So we have a guided wave region, transition region, which we call antennas, and then space waves. So that's the whole story comes about. So how do we quantize this a little bit? So it is amazing that nature detaches electromagnetic waves from antennas and allow them to propagate in space. And that is amazing. That we have seen that in our courses, we talk about it, we read about them, but we never sit down just quietly and think about it. How does this happen? That this electromagnetic wave detaches themselves from antenna. Once they detach themselves, then propagate forever. And if you look at the special theory of relativity, that's exactly what it is. Because when these waves or lights or electromagnetic detaches from the source, then the speed is constant, no matter what the source is doing with respect to other reference directions. So that detachment going to space is the key. So we want to make that effectively and efficiently. So typical antenna parameters. So you can actually divide it in three pieces. You can have a circuit elements that many of our colleagues in MTT are more interested in. We can have an antenna part transition, kind of work that I'm interested primarily, and then space when this radiation occurs. And then when you look at this, you can put these notions: radiation resistance, antenna temperature, efficiency, and so forth. When you come to the antenna, it can be how the current distributes on the antenna, because ultimately this time-varying currents is the source of the control radiation. And when we look at how to represent the radiation, we typically talk about the far field patterns, beam area, directivity, gain, and so forth and so on. And of course, all of them ultimately use in Friis's equation to create an effective communication link. That's what we are interested in. Among all the things that might be of interest to you guys in particular is the notion of impedance mismatch and VSWR. So in general, an antenna's input impedance does not match with the impedance of the transmission line or guiding structure in general. In order to reduce the mismatch and prevent loss due to the back and forth reflection on the transmission line, matching networks are typically used if it's needed. Matching networks takes many different designs depending on the antenna configuration, transmission line, bandwidth objectives, and so forth. So that shows that we want to deliver all the power that we are generating, spending money into the space wave. If there's any mismatch, some of this power bounces back and doesn't get radiated. How we quantify that? We quantify that by this parameter S11, a very important design parameter. So good S11 means high percent of power is delivered to EM waves. That's what we want to do. So if you look at this chart, this shows a return loss in dB. This is a percent of the power transmitted or delivered to the electromagnetic waves. As you all know that typically this 10 dB return loss is a good reference point, and the reason it is because that tells you about 90% of your power that you have generated gets delivered to space waves. Probably many applications you want to do even better. If you go to 20 dB S11, 99% gets delivered. So, and in some applications you cannot get this. As a matter of fact, a lot of cell phone related applications, you might be working in the regime of 6 dB S11, so you allow more loss because that's all you can get. Antennas are too small, too much interaction with the human, and so forth and so on. But this is the key parameters that periodically I may refer to that when we talk about different antennas. And finally, definition of bandwidth. And bandwidths are critical, especially in the more modern areas, or multi-band, broadband, ultra-wideband, and so forth. Two definitions should be appreciated. Typically, when we plot VSWR or S11 versus frequency, and if we use the reference point of minus 10 dB or 10 dB loss, and which is the same as VSWR2, we have a lower frequency and upper frequency, and then center frequency, which is the average of these two. So the bandwidth then defines on the ratio of this upper, lower, divided by center, so that we say this antenna has 10% bandwidth or 50% bandwidth and so forth. Or there are occasions that the antenna might be very broadband and might be octave or bands, so we just use the ratio because this definition may not be as useful in these cases. So then we just look at the ratio of the upper and lower frequency we usually use for large bandwidth antennas. So we now, when we talk about antennas in a little bit more detail, these two issues, S11 and bandwidth, are something that we have to keep thinking about them. So in my group, we have done a lot of different antennas. We were some of the first one who looked at the interaction of the cell phone antenna with human, and that was published in 1995 and appeared on the front page of the proceedings of the IEEE. And we have done a lot of work antennas for space application, for NASA work, interaction of antennas for laptops, antenna measurement. So if you are interested, you can really look some of these publications in detail. So antennas can be very large, and we're talking about this is a Cassini mission, which is now in orbit, orbiting the Titan, one of the moons of Saturn, and this was a 4-meter dish operating at 2, 8, 14, and 32 gigahertz. Huge, almost 2-story big spacecraft. There are some future missions for NASA we are looking, 6-meter for the precipitation radar, 13 and 35 gigahertz. Mapping hurricanes, this is some new projects that we are hoping that bring it to the next level. There's a 35-meter dish in space operating at 35 gigahertz. You can imagine how complex it is, and some radio astronomy application. But what is the interest for this forum? Antennas can be very small. And these are antennas that we deploy on different gadgets. It could be small ultra-wideband antenna for medical application, cell phones, MIMO, and so forth. So today we are going to focus more on this aspect of the work. One important parameter of concern is the miniaturization, because everything is getting smaller. You want to get as small as you can, and how would you achieve that? But there are some also physical limitations. So link budget is the matching, radiation efficiency, and directivity. But then there is also this important observation that people have made, especially Professor Chua from MIT many years ago, is the bandwidth, which is fundamentally limited for a small antenna. So you cannot forever expect high bandwidth and very small antenna, and that's where the struggle is. A lot of research is going on in the metamaterial and so forth to improve this Chu's limitation in particular. And then when you look at the information capacity of a wireless system, again, you go back to Shannon's law, and this is the maybe last equation. So there are several items that are embedded here. Number of channels, diversity, bandwidth of the channel I, and so forth and so on. So to improve the capacity, what can you do? If you just close your eyes and say, what can I do to improve the capacity, which is ultimately of interest? You can use a broader bandwidth if you can. That may pushes you towards ultra-wideband communications. To use higher transmitter power or antennas with higher gain or more selective beam, that may push us towards the adaptive beamforming antennas. Or you might exploit more number of channels or diversity, and that might be pushes you through diversity techniques and MIMO. So you try to utilize all these capabilities in some creative fashion to ultimately maybe improve your channel capacity, which ultimately you are interested in. Now, if you look at this wording here, it's very paramount for what we are discussing today. It says, the bandwidth of an antenna which can be closed within a sphere of radius r can be improved only if the antenna utilizes efficiently what is with its geometrical configuration, the available volume within this sphere. In other words, if I have an antenna of given size, I encompasses this antenna by a sphere with the radius r. So if this is my flat antenna for my cell phone, from the center to the edge radius r, I put a sphere. You can see that sphere is not filled in. When that sphere is not filled in, it reduces the bandwidth. So that's why if you see there are a lot of times people are looking more volumetric antennas if the space is limited in order to fill up the space. And when you fill up the space, you can improve the bandwidth. So this is some of the guidelines that people look, as we'll see some examples shortly. So in practice, many low-profile planar antennas do not fill the space effectively, and so they don't work with. So what is the challenge then? The challenge of miniaturization are several. You have to ask yourself, some of you who are maybe more in tune with antennas, if not in the broad picture, I'm trying to bring my presentation to your attention. You ask yourself, is the antenna electric type or magnetic type? For example, if you have a dipole wire antenna, inherently you can see it's electric type because the current goes. If you use patch antennas, even though there is no magnetic current in nature, but it doesn't preclude us to think about an effective magnetic current. So edges of the patch antennas create effectively equivalent magnetic current. So patch antenna could be considered as the magnetic type. Are these antennas in resonance or out of resonance? Are they low profile or low volume? They're different. Sometimes you design antennas which are very low profile, but may not be miniaturized in all 3Ds. With or without ground plane, are the antennas has to support ground planes that patches typically necessitate? Are they single frequency, multi-frequency, narrow or broad bandwidth, single or multi-element, static or reconfigurable, low cost or high cost? So these are all the questions that one has to address. So some of aspects of this I'll try to touch upon here and there. But potential approaches for miniaturization. So this is where a lot of research is going on in many different institutions. Potentially use high dielectric constant to reduce the size of the antenna. You might use double negative or metamaterial to inspire from these concept that your epsilon and mu are negative. Even nature doesn't have it, you can create them, and that might help you to miniaturize. You use low-profile antennas using electromagnetic bandgap structures, folding antennas, structure profiling fractals, incorporation of switches, that the hybridization of the above is stored energy utilization. So we are going to see some representative example, just to give you an idea where the research and activities are going on. Some of them are already deployed, and some of them hopefully will be deployed in the future. Okay. So the winning approach for an effective design and optimization of novel antennas, I'll put them in some kind of Olympic rings for you, 5 of them. Nowadays, because of power of a computational and optimization techniques, there are people, vendors in this conference. It allows you to do a lot more than we did in the past. Electromagnetic visualization have brought a new paradigm for us to understand what is going on. It is not just you run your numerical techniques, but with the visualization, you can get a lot more physics of how this current runs on different pieces of antennas, how the field behave near the antennas, and what is the interaction with the environment and so forth. Performance measurement, very sophisticated measurement techniques, novel antenna design, and antenna characterization. So these are 5 Olympic rings. If you have them in your capabilities, allows you to develop novel and out-of-the-box type designs that we are going to talk about a little bit more. So if you again go back to this proceeding to IEEE, which was in July of this year, 2012, they talk about advanced computational techniques, advanced nature-inspired optimization, and modern measurement. So I'm going just to relate to that. So in our capabilities, as many other, we have actually combined very advanced electromagnetic simulation tool with the state-of-the-art optimization. For example, we have an engaged or integrated method of moment solution, find a different solution, you name it, with this nature-inspired optimization. So, of course, I'm not going through the details of this. Just to bring it to your attention, there's a lot of powerful capabilities nowadays available through vendors, through researchers, to be able to evaluate electromagnetics phenomena from antenna to the wave and to the what is going on in the space a lot more effectively. I'm going to talk a little bit on this computational part, which could have some novelty for you. And this is, I'm going to talk about just a few words to bring you to the state of the art of some of the optimization. Fundamentals of particle swarm optimization, and I'm going to use the abbreviation PSO. And the original concept was suggested by Kennedy and Eberhard in '95, and our group was the first one to apply it in electromagnetics. And as a matter of fact, since then, a lot of people have got interested into this. We wrote a paper in, 2004. It was a tutorial paper if somebody is interested in the IEEE antennas and propagation transactions. And my co-author of this paper, the reason I'm showing that, was an undergraduate student. And among all the papers I've written, you heard the numbers, this paper has the most number of citations. As well, this is old. The latest citation is over 1,200. Which, I was very fascinated that I had this brilliant undergraduate students working with me on this particular work. So what is the big picture of PSO? Relying on the observation made on the social behavior of swarm of bees and a school of fish, it has been conjectured that the collective intelligence of swarms directs them to look for the most fertile feeding location. So then the question is that, can we use this potential activities of the nature into engineering disciplines? And so I used the bees as a manifest of this concept. So with this acceptance, let's assume this is true, it has come the temptation that perhaps one might be able to utilize swarms searching mechanisms and apply it to the solution of engineering problems via the application of particle swarm. So I'll just give you a 2-3 overview about the concept. So I think the concept is depicted very well here. Let's suppose I have this cost function, two-dimensional, in general can be multi-dimensional, and I want to find the global peak in reference to some local peaks. So if you use any standard methods, they all get kind of stagnated, and this local peak, you may not ever find your global peak. So let's suppose this is, if you look at it from the top, this is a contour. So what happens that I randomly position several of these bees, there are potential solution, and I then let these bees communicate together. And the two features, what is that nostalgia as the bee fly, where did I have the best reference that I had a good remembrance where there was a lot of flowers, I want to go back. But at the same time, I'm using the social characteristics of all these bees. All the bees talk to each other, and we found that this time T, this guy, that bee has the best location in terms of where is the most fertile flowers. So we all try to fly in that direction. So two forces, nostalgia where I had the best experience, and social knowledge that who had the best experience at given time, redirect these bees. So as they fly, they re-evaluate themselves. So this collection of the two forces brings these bees to the peak. You of course need one of them to get to the peak, or any solution that desires, and you say you are done. And so we have developed algorithms for this, as many other people have. And this is not us, many other people have done that. So you can put this concept into an algorithm. So if you have an antenna to design, it has 5 parameters, it's a 5-dimensional space. You deploy randomly bunch of potential solutions, albeit they may not the solutions that you want, and then you let this solution evolve by this interaction and hopefully bring you design that you are interested in. So I'm going to show you some examples. It's very different than genetic algorithm, which relies on Darwin's evolutionary and competition processes of the best fitted species. This is more social interaction of the bees to bring them to that. So we have developed all these different techniques, and we have written books about some of them in our work. So what are the winning features of evolutionary optimization techniques? I just used this bird's nest when they had the Olympic in Beijing, China, and I put another 5 rings here. These methods have 5 essential characteristics. They do not require the knowledge of derivative of your cost function. And that's important because any other seeking methods, you have to find the derivative. Here you don't have to. Sometimes your cost function may not be differentiable. You don't need it. They can work with the continuous and discrete parameters. It can be binary coding or can be a real number coding. And they are very suitable for parallel computers. And they try to look for global optimum. All of these nature-inspired techniques would do that. And most intriguing is the following. You can get solution may not be not intuitive. So after you get them, you may reflect on them to see what is the physics of this solution. But sometimes you get the solution that you might not have thought about. And we'll show some examples of that also. So how long does it take to get the optimized result? So that's always the question. When you do optimization, can you do it in 1 second? Would it take a year to do it? And so forth and so on. So in order to respond to this question, one may say the following. Depending on the nature of the problem being optimized, it could be seconds, minutes, hours, or days. It's possible. But sometimes it's okay, because if you look at occasionally, it is worthwhile to wait for a long time to get the best product. And many of you have that experience. If you, in a good wine, it takes a long time to produce. So sometimes we are pushing ourselves. Everything has to be done in 1 second. It's okay if it takes a day. If you get a very good design, might be worthwhile. If it makes your boss happy, maybe it's worthwhile. So it depends on the nature of the problem you are solving. You might encounter different time frame. But fortunately, you can improve on all of them. These techniques are so natural to be deployed on parallel computations. In other words, the time which takes to do these optimization profoundly affected by your computational tools. For example, if I'm designing this patch antenna, I have 5, 6 parameters, and I have to go and do my computation, find the different time domain method of moments. That's the part it takes longest time. So I can deploy all these B's, potential solution, on different machines, and we call it the slave nodes, and only communication link comes back to the master node. Master node then decides where the new bits should be located, a new design should be considered, and deploy them again. So you can almost reduce the computational time almost linearly by the number of the slaves node that you use, and that we have used in our work. So with master node tracks particle position and velocities, tracks the global best, applies update equation, reads configuration files and prints and so forth. And the slave node gets the particle position from master and then performs simulation and fitness evaluation, return results to the master node. So all these capabilities can be used. So we have used these computational tools and these optimization to address many different problems in radio astronomy, in remote sensing, personal communication, medical, and nowadays we're working on some nanostructures, optimized nanopillars, and so forth. So today, I'll probably give you an example from the personal communication and medical. So yeah, I think I'm doing fine. So don't worry about this time. I started at 8:45. I try to finish before 10:10. So the next story is innovative wireless antennas. Now that we have the framework of the capabilities, now that we have the framework optimization, how would we use them to solve some interesting problem for the communication application in particular? For example, I'll just give you a design. So we wanted to design a patch antenna that tunes at the 2 frequency, 3 and 4 gigahertz. By tuning means that at these frequency, you want your S11 to be better than minus 10 dB, as we talked before. In this case, we call this antenna is a dual band because it operates effectively at 2 bands, but we can also talk about wideband and so forth. And this has come from this optimization. So I started from a patch. Just imagine that this is a full patch, no holes in it or anything. And I let this evolutionary optimization evolve the shape of the patch by saying that if it's a hole, it's a 0. If it's a metal, it's 1. So I use the binary coding. And then I designed this. And after it was finished, the patch came to be this shape. If you recall one of my Olympic rings, you get the designs that you may not have intuitive feeling why that design gives you the performance. And indeed, you would not have thought about this design, but by just these holes created and the patch got configured like this, when we measured, this is the measured data, this is simulation method of moment, simulation for different time domain, and we got very good correspondences. So it demonstrates that we can design things that before might have not been very easy to talk about. Of course, you can start to look at this and see how this works. You can interpret some of these things and stop tunings and things like that. If you want to give a physical interpretation, the mechanism of operation for this patch. But this is a simple one. So let's see if more sophisticated one. We invented this E-shaped antenna, which has obtained a lot of attention in the literature because this can give you a wide bandwidth or multi-bands. So this E-shaped antenna have many parameters, over 10 parameters. So we do that through this optimization method, and this shows the convergence, how many iterations you have to do in order to get the solution. And depending on the design, we have design antennas which might have a dual band or can have a broadband. And for patch antenna, this is probably one of the widest bandwidth patch that people ever put together, over 30% bandwidth. For typical patches are 4%, but this is over 31% bandwidth. Then we deployed all this concept for some modern application. We did a lot of work in the past on the application of the cell phone and interaction with the human. So this is a classic whip antenna, and then we look at diversity antenna and so forth. So we called this particular class of antenna, this is the early 90s, and you go back almost many years, many decades back. We call this back-mounted when we introduced the concept. Now people refer to this concept as internal antennas. Unfortunately, UCLA wasn't so excited those days to patent these things, but that's okay. So now you can see a lot of antennas have, cell phones use different formation of these, which we call internal antennas, by just bending the metal because you have so much room constraints and so forth and so on. So we said that can we use our optimization techniques and even evolve with more weird-looking antennas, and indeed we did. So we did the optimization, and we said we have so much space on our cell phone. We wanted optimization to give a design, albeit weird-looking shape antennas, in order to do a particular performance. So here we use a hybrid parameterization. We have a real number for this part, which attaches to the transmitter, receiver, or whatever, and we have a binary for the shape of the antenna. And collectively, this is an optimization over 100 parameters. 100 parameters, dimensional space that we are optimizing in order to get the best design for particular performance. And this shows again how this process converge, maybe near 200 iterations. And this is that particular weird-looking antennas. I told you, you make the designs that you a priori don't have any feeling what it is. Again, this antenna was designed to operate at 2 bands, and again, measured results versus simulation, it showed it really operates very well. And now you can go and look why it's doing what it is doing. So this is a 1.8 and 2.4 gigahertz. So we wanted to see what pieces of these antennas are doing most of the radiation at different frequencies, and indeed you can now go and look deeply. And that brings me on the other ring of the Olympic, visualization. Because electromagnetic visualization would allow us to understand now the physics of operation of some of these very different class of antennas. And just show you some other representative. Other designs we have looked for MIMO application. This is a very small deployed MIMO application to operate at the frequencies of interest. And this we call 2-element and 4-element PFA, planar inverted F antennas, which are very popular class of antennas, which was designed and fabricated. And so if you look at this particular design, again, weird shape of that, allows us to tune at 2.4, 5.2, and 5.7. And again, this was built and measured and so forth. And again, you can do visualization and see what piece of this antenna contributes to radiation at a particular frequency. Again, gives you more insight of talking about these antennas and their physics of operation. And these are different these antennas, we developed 4 of them. We try to measure all of them just to make sure they all work effectively. And then we had a very nice test bed for MIMO evaluation of these class of antennas, and this MIMO test allows you to look at the capacity and so forth and so on. And this is in collaboration with other faculty who are more in the communication domain. So channel capacity response measured and so forth and so on. Now, I'm now going a little bit more into the application oriented. So we use these concepts also to look at the MIMO antenna developments for laptops, possibly. Not only we look at the laptops by itself, we look at the laptops with the entire device, and also interaction with the human. And these are, again, some of the capabilities now you can develop and understand what is going on. So here, for example, it shows the, I don't know, this is supposed to rotate, but maybe here it is not rotating on this computer. So we look at the antenna by itself, antenna mounted on the laptop, and antenna mounted on the laptop in the vicinity of the user. So this rotates. You can see profound difference on the radiation characteristics. Why is that? The reason is that when these antennas radiate, that radiation oscillates electrons in your body, and oscillating electron, which are essentially means time-varying current, radiates, so your body is part of the antenna, and then collectively, together, that's what defines the radiation pattern of this system. So clearly you can see in the back, due to the blockage of this human, you don't get much signal going to your antenna from the back direction. But now, these capabilities are available to understand what is going on. Oh, actually, this one shows you. So this shows you patterns from different angles, from the front, from the back, from the side, and so forth. And the key point to be amplified, when you look at the antenna gadget by itself, it's just a typically dipole type pattern, 2 lobes. When you put it on the chassis of your laptop influences, and if you put the human, influences more, and you have to understand all that in totality. So we also have looked at the specific absorption rate for some application, what part of the body might be absorbing the most of the energy at that particular frequency. So these are some of the characterization. So visualization, again, tells you what's going on. It could be a specific absorption rate, average over 10 gram of body, or over 1 gram, depending what the particular system that you are considering for evaluating the performance. And if you go through that, this particular design was very unique. This was our E-shape, but folded E-shape on both front and back, because for laptops it's most critical you have almost the omnidirectional pattern in horizontal plane. So this design allowed you to achieve such a performance that we have talked about. So we call them back-to-back E-shaped patch antenna mounted on the edge of the laptop. So this is one design. People have other designs, of course. And we also designed them to work at 2 frequency, in particular 2 gigahertz and 5 gigahertz. And depending how the currents, what frequency you are, currents take different path. Because ultimately, this time-varying current is the manifest of the matching properties of the antenna and radiation characteristics. So at some frequency, the currents might take shorter path. At some frequency, they might take longer path. And that allows you the antenna to be tuned at 2 different frequencies. So these are, again, if you have an inside understanding of your operation, so you can say why this antenna is doing what it's doing. And we look at a bunch of scenarios, how you open your laptop, what angle you open your screen, and so forth, and its effect on the performance. So this was a collaboration with the team in one of the university in Portugal. So we have a lot of collaboration of this nature. So this gives you, again, the feeling when this antenna was mounted, how the radiation, how the electromagnetic currents kind of propagates on your laptop, and how the radiations occur from different pieces of the laptop. And again, as we noticed that how the overall performance can be observed. And most interestingly, this kind of chart So you can see, if you see it in the front of this, at given frequency, how much energy gets deposited in the body, a specific absorption rate. From the safety consideration, these are important issues, in particular towards the eyes and so forth and so on. So we are able to quantify these numbers. We are not the ones to say what is bad, what is good. Hopefully medical people or other people would use our information and assess its implication on the health consideration. So don't show too much. It's just a graphical presentation, a different angle of opening of the screen, and so forth and so on. Now, just a few words about specific absorption rate. The specific absorption rate is the measure that how you heat up the tissue. This is not the ionization, because the frequency is not at X-ray or gamma ray and things like that. We believe it doesn't ionize, your metabolism or whatever you want to talk about. This is if there's any problem, it's just the heat. So in order to quantify that, we use this notion of a specific absorption rate. So essentially what it is, as you know, every part of the body, skin, bone, brain, and so forth, they have different conductivity. So if you want to see how it's kind of Ohm's law, essentially. So if you know the electric field intensity at the given point inside the brain, inside the body, then you say sigma E squared is the watt, this is the heat, and then you divide that by the mass of that little piece that you are interested in. So typically the unit is milliwatts per gram. You average over 1 gram or you average over 10 gram, depending what the standards you use to evaluate them. So recommendation is that the specific absorption rate should be less than 1.6 milliwatt per gram, and no more modern cell phones, they try to write it small numbers in the back of cell phone or in the manual just to see what there is. Now it is mandatory that they actually use very sophisticated measurement apparatus to evaluate the radiation properties of different cell phones in the kind of a human look type mannequins, which they have very similar electromagnetic characteristics, and measure to see what the specific absorption rates are. So there's a lot of research is going on. There's a lot of debates. Europeans are, in particular, a lot more concerned than we are in the US, but this debate is going on probably for a long time before finally we come to some more critical conclusion about the health effect. So for example, if you look at this example, you are able to identify the SAR at different locations and so forth and so on. Now, we also did some actual deployment in our anechoic chamber at UCLA to do some measurements. So this is your laptop, and this is the screen. This is a representative screen with some antenna mounted at the edge. Then we did the measurement. These are actual measure results, and they correspond very well with our simulation. And then we evolved that to some MIMO deployments. So we have a 4-element MIMO that was integrated with the edge of the laptop and so forth and so on. So just show the nature of the research is going on. And we can use very sophisticated human body model. This is a slice of 1 millimeter. We know the electromagnetic properties in terms of permittivity, conductivity, and so forth. And we can do these models on the computer nowadays very effectively. And this work actually came on the cover page of the Antennas and Propagation magazine several years back, if somebody's interested to look at it. Now, let me evolve a little bit where we are going more in the future. We now move from external to wearable and implanted antennas. Now, because the medical domain are very interested to have this wireless communication. We already talked about this external, handheld, and so forth. I say a few words about wearable and some medical consideration. Again, there is a book published by Professor Hall and Howe on antennas and propagation for body-centric wireless communication. And we had a chapter there about this wearable antenna and so forth. What really is, people are looking at deploy antennas on the clothing or other parts of the material that you carry on you, and try to use that as a node for communication link, either to base station, to your cell phone. I don't know how sophisticated with satellites, perhaps not, but other utilization. So the question is that how these antennas perform when they're deployed on the kind of a material which they can bend and so forth and so on. So we did a lot of research in this area just to let you know. In particular, these areas are interested for astronaut suits, emergency workers outfit, military applications, soldiers on the battlefield, and also medical applications, sports, entertainment, and so forth. So again, just to bring it to your attention, some of the areas that some interesting work is going on and could be of interest to the people in this forum or other forums. So we have developed a very sophisticated strategy to design these antennas, from the single band, multi-band, what kind of fabrics you use, do you use some more sophisticated antenna concept, consideration to the specific absorption rate, because some of them might be even active units, and then elasticity and electric properties and so forth. So it's a very complex paradigm to develop these antennas on these more sophisticated environment, but work is going on them. So these are just some samples as a starting research part. Depending you use the copper or use some other material that we are working on, I'll show you some example. And depend how you deploy them, are they seamed or they are is it knitted copper, or is it fabrics or metal netting, and all these different designs have been looked in order to evaluate their performances. We also look at if you put it on your arm is kind of a curved in one direction, the effect of the curvature on the performance. So I just want to tell you the story is not as simple as it sounds. You have to worry about all these little nitty-gritty aspects of the design, which we have done. All right, so this, for example, shows dependence on the curvature of the arm cylinder. So you want to have a designs which not be very, not readily affected by these environment proximities. So let me, we have a look at some more complex structures. And so let me move to another aspect. Another interesting work which could be of interest to this community as well is we have some collaboration with the university in Finland, and this is embroidery antennas that you actually sew on the cloths and things like that. So we have actually very interesting research is going on this. So this could be for RFID application, for sensors, healthcare, biomedical application, or it could be for biological tissue absorbed RF and its effect on the performance of this class of antennas. So what it is, it actually, our partners in Finland, they use some sewing machine, a Viking embroidery machine, and they actually sew these antenna patterns on the materials. So first we designed the footprint of the antenna here for simplicity, a dipole with some matching ends, and then here we put the chip. This could be any of the RFID chips, and then we want to evaluate their performances. So this is one typical design consideration. So first we developed, if it was completely copper, as best antenna as you can get, what the performance is. Typical, when you talk about RFID, you really care about the range. How far can I communicate with the chip, that if I send a signal and chip reacts back and tell me that what is going on with the chip information that I'm trying to collect through RFID type identification. So here, for example, this design manifests about 10-meter interaction. I forgot exactly what chip we use, but these are more modern chips that they have a good dBm characteristics. So then we develop different version of this antenna by different pattern. So some pattern has some zigzag, some pattern was less zigzag, and so forth. And this was our original copper. Of course, we don't get as good as original copper, but it's still the read range was about 7 meters, which in some application can be pretty good. So the sewing pattern consists of the sewed line along the length of the dipole and zigzag sewed on top of it. Zigzag density does not significantly affect the performance of the tag antenna embroidered as we have demonstrated. Actually, our team very recently developed that on some jackets, and they put it in the washing machine. They went through several cycles of washing because you have to make sure they survive. And indeed, we just had a paper recently on that. I don't have time to present those data, and it showed it really sustained its performance pretty good, the way it was put together. We also have done the actual measurements in the activities we had with our partner in Finland to measure the read ranges and so forth and so on. So this is one of our collaborators. We have some paper with her, Carolina, and she actually put it on her arm. And this is a reader for the RFID, and we measure the range and so forth. First on this, let's say, a metal strip, and then actual embroidered system. So we think this is an area that could be of great interest in the future deployment of these techniques. All right, so let me, okay, we are just reasonably on time. No, pretty good actually. Now I want to say a few words about medical, because this looks to be really an area of a great interest. When I travel internationally, there's a lot of interest in Europe, Asia, and so forth on this. And this is the whole notion of the biotelemetry. Ultimate goal is that managing care through the air. That's the ultimate goal, managing care through the air. The intent is that you want to keep contact between you and your physician. And one scenario people have looked at, it could be implanted devices or others. They communicate with your cell phone, and your cell phone may communicate with the base station, and ultimately you get connected to your hospital and to your doctors. So the link, understanding the propagation from inside the body to outside of the body, and also understanding how energy propagates along the body. This is a body-centric communication concept. These are all very critical items in order to get this technology off the ground. I believe some other speakers might be talking about this a little bit more. We had a little book, Implanted Antennas in Medical Wireless. If somebody is interested, you're most welcome to look at it. So the key aspect of this work, that at least at the phase of the modeling, you have to have a good model of the human, and depending where you put these devices and you want to create a communication link, that allows you to understand the performance. So this is one design of a spiral planar inverted F antenna. Here we are using the frequency band of 402, 405, which is dedicated for this application. There are other frequencies. There are frequencies L band. Now also there's a frequency at S band for this medical application potentially. So the whole goal is that to miniaturize them as much as we can. This is not super miniaturized yet, but we are working on that. But in order to show it works, we just want to make sure even with this small size unit, we can get some performance that's acceptable at this frequency with enough bandwidth which allows you to operate in this band of frequencies. And such antennas were developed, and again we put it inside the body to see specific absorption rate. So the power level has to be very low in order not to have a high heating of the tissue near these antennas. And we are looking at the radiation pattern. Of course, the efficiency of these antennas are very low because the signal, when it propagates from inside body to outside, gets absorbed quite a bit because the body has a lot of water in it. And water is a conductivity. When you talk about high conductivity near 50, a lot of absorption happens, especially at the higher frequency, even worse. But we are able to evaluate these things pretty effectively. As a matter of fact, if you look at the most recent IEEE Microwave magazine just came out, there's a big section on these biosignals. And in that section, they actually refer to our design that we put together in 2004, which was published in the IEEE Transaction Microwave Theory and Techniques. And so this article, as a matter of fact, it's a nice tutorial article just came out about this whole biosignals and so forth and so on. All right, very good. So let's see what will be the next evolution. So we are evolving. So we did the handheld, we had the wearable, we have evolved to implanted. What is next? The only thing is left, ingestible. So can we really eat our antenna and have that communicate with outside world to do diagnostics and also to do some other interesting performance. So I want to say a few words about that. You know, this is a biotelemetry, as we said, is a very popular activities nowadays. And it's in telemedicine. As you know, there are a lot of interest in this wireless capsule endoscopy. Instead of using the tubes, you want to use the little capsule to interrogate what's inside your body, your stomach, your colon, and all that. And so that's one of the areas that we are getting interested. As a matter of fact, we are collaborating with some physicians and medical doctors who are also professors at UCLA to go more deeply in this area. So if you look at endoscopy traditionally, scope test would only achieve imaging of about 10 out of the 30 feet of the digestive tract, the upper 4 feet of the stomach, and the colon and the rectum, leaving the remaining 20 feet of small intestines probably unexplored. What this new paradigm is to have a very sophisticated pill that allows you to do some mapping. It could be optical mapping, and I'll talk about also sensing later on a little bit. So the challenge is to design a miniaturized antenna with effective performance, because these pills, when it gets swallowed, goes inside your body, they may tumble, the polarization may change. So we want to come a design which allows us to have effective communication with the outside world. So we have actually looked at that. There are many constraints on this design. Physical size constraint, the location and orientation. The capsule have many electric components in general, and so forth. And this particular work, we are looking at this band of frequency, which is dedicated to WMTS frequency. So just to give you an idea, we started from a simple concept. You see, the pill is supposed to go inside and hopefully goes to your wherever it's supposed to be mapping. So we started from the simple dipole with the off-center fed, which allows you to shift the frequency. And then, of course, this will be too long, way too long. Good match, but too long. And then we miniaturized that by meandering this, so it's smaller, but it doesn't conform to the capsule. And finally, we came with this design. We called it the chandelier look. And this is this folded version of this meander dipole, which can be mounted on the top part of the capsule for this, which does a lot of interesting things. Conformal miniature design, good matching, we talked about that, polarization, diversity, and easy tunability inside the human body. Because if you design your antenna outside and you put it inside, the performance gets degraded quite noticeably. So you have to design that with the anticipation what the interaction with the body is inside, and we are able to do that. And we tested it just idea-wise and so forth and so on. So I don't go through all the details. But just to show that we are using the second frequency, which is now around the 1.4, the frequency of interest for this implementation. So this is ongoing work, and we are working with other colleagues to hopefully bring it to the next level. And this is one of the concepts that we had. There are already the pills available with some other antennas, but they don't perform as effectively as we believe with this new class of antennas that we are hoping to deploy on this very small capsule. You're talking about 1.5 centimeter or smaller, just typical capsules that you have with your medicine. And we look at its performance, the radiation characteristics, and so forth. Again, if you look at the paradigm I put together, what is a good way to design antenna from simulation, optimization, visualization, measurement. So we use that 5 Olympic rings in order to complete a particular design for particular applications, of course. And then we look at where this might be different parts of the body, stomach, colons, and so forth, and see how it performs with outside world. As you notice that the detuning could occur, but now we can, because this antenna design, that by changing the length, you can retune them. So now we know what part of the body we are expecting things to be most effective, so we can tune the antenna for that part of the body and get the best performance and bring a frequency back to where we want to be. We look at the other features of these capsules, so I don't want to go through all the details with you, but just give you an overview. So just keep on going. Effect of electrical components. We look at the electric field distribution in terms of, in particular, polarization, diversity. So this shows the capsule inside the stomach, and then depending what orientation the capsule has, we want to make sure still we get a good electromagnetic performance with outside world. And we look at the radiation power distribution in the front and back inside the body in order to assess the health consideration for specific absorption rates and all that. So, these are, again, referencing to some limits that you have to consider. Of course, bear in mind, the radiation efficiency of this antenna can be very small. We're talking about less than a 1% efficiency. Because it's not just the antenna. Antenna might be efficient, but when it's inside the body, most of the energy gets absorbed in the body. But when you have a communication link with the outside the body, what comes outside the body you care, but not so much what's inside. Inside, from a health viewpoint, you have to have that limits. But from outside, that determines your communication link and data rate that you can utilize to do the job. So we have done that. So if you do the link budget analysis, like a Freeze's type equation, that ultimately tells you how it works. For this class of application, people are not looking very high data rate. We are looking at data rates maybe in the regime of megabytes and things like that. So then when you look at your link evaluation, you have to see if you have enough margin to be safe. And indeed, we have shown that with design that we have in mind, antenna performance that I have brought to your attention, we should be able to have a reasonable communication link with the outside devices that we communicate to if they are in the regime of 2 to 3 meters or about that distance from the human. That will be the monitors that allows you to at least get a reasonable data rate to tell you what is going on. So again, these are ongoing research work which necessitates very sophisticated antenna design for these bio applications. All right, and then these are some of the work is going on how to deploy them. At this stage, it's just a research, of course, but we hope that we can bring it to the next level in the batch fabrication, make it inexpensive, and side micron control to film thickness and things like that. All right, so let me don't go through all these details, but these are typical capsules we're talking about, and this is how it deploys, and hopefully we get it all working. Now, there is another very important paradigm. That's the bio marker. So the other one, you took images, but there are a new front which comes, and this is really a most exciting front, I believe. And that is using a sensor on these pills, and these could be nanosensors. So when you deploy these capsules inside the stomach and whatever, these sensors tells you if there is a potential of ulcer or other diseases that might be coming about. And that's, to me, it's one of the new paradigms in medical diagnostics. And a lot of interest is going on. So we are collaborating with some our colleagues who are more in the part of the sensor. So these sensors sense the chemistry, whatever, and then our system allows that information to be communicated to outside world, and that can be very important from the view of the preventive measures and health considerations and so on and so forth. So this is the actual dream, if we can come to this dream as well. So these are nanosensors. These are nanowire biosensors. They sense what's going on. They give that information, and the capsule may not be as sophisticated because we don't have necessarily optical system to image. You could, but you don't have to. And then we communicate to outside world. And in order to get that even work more effectively, we like to see if we don't have to put any batteries, because typically there are small batteries inside this capsule. If we can use this wire power transfer, so electromagnetically power these units and then do the communication link. So it's a pretty ultimately sophisticated system, but has a lot of intriguing research components to it to bring it to fruition from many different angles. Okay, so, and One more item on this, then I think I can allow a few minutes for if there are any questions. So this was all the medical diagnostics and sensing. There's also medical monitoring getting attention. Because it is known that the older people, sometimes they don't take their medicine. So there are gadgets available. When you take the pill from this gadget, it registers, but it does not necessarily tells that the capsule is taken. So maybe capsule is dropped or hidden under the pillow and things like that. So you don't know if it's used. So we are looking at some monetary system through this RFID concept that when the capsule is swallowed, it gets registered. So that's actually pretty interesting. They are very sophisticated capsules, so hopefully in time they get cheaper and more productive in terms of understanding if it's utilized properly or not. So we are looking at the interesting concepts that we monitor. So this is, again, the capsules that integrated with some RFID chips. This is more RFID now. This is detecting if that capsule inside the body is taken. And it's very intriguing because this capsule doesn't work well outside. It's only tuned when it's inside the body that this chip would have most interaction with the reader. So what is a reader for this? So we are actually forecasting, if I go forward a little bit, so this is the typical chip, this is Alien Higgs 2 or maybe more modern one, 3 can be used. And all those, because now these antennas has been designed to conjugate match with the chip. So it's not the 50 ohm any longer. It should conjugate match to the chip impedance, which itself could be 40 minus J, 145. But we can do that. We can design these antennas to conjugate match to the chip in order to have the best interaction with the chip, antenna, and outside world, of course. So what we are, so these are some radiation pattern of the capsule. If it's at this location, that's where you swallow. We want to make sure we can detect that this pill has been swallowed and so forth and so on. And so we have done a lot of work in this area. There are a few more items I probably bypass in the lieu of time. And these are ultra-wideband frequency antennas and so forth and so on. So I may just say one word, if I may, about the, let me see if this works. I want to jump over some of the view graphs here. Here. Yeah, on the metamaterial, just one or two words. You probably have heard a lot about metamaterial. This is a paradigm that's getting a lot of attention. The word meta means beyond the nature or non-existing in nature, broad interpretation. And in our community and antennas on propagation, MTT, and physics community and optics, they have different angles to this. So they could be artificial complex ground plane, there could be electromagnetic band gap or double negative material. And if you look at the time signature, how these things has been developed, some concepts of these were available in 1940s from filter viewpoint, band stop and band pass and all that. Some aspects evolved in 1995 with electromagnetic band gap, frequency selective surfaces and so forth. So these concepts are starting to get a lot of attention in our antenna community for miniaturization and getting antennas that before we couldn't work with. So we have done a lot of work, even we have written some books and many other people. The time is short to go into this, but if any questions, I'll be most happy to entertain. For example, one is on the miniaturization. So when you miniaturize a patch antenna, one way to do that, you put that in very high dielectric constant material. But then when you put in a high dielectric constant material, the bandwidth very much depends on the height. So if you make the height higher, you get more bandwidth. But you pay the price because now you allow some surface waves to propagate. And then the surface waves propagate, they radiate. Then you have space waves, they radiate, and they interfere. What really happens that when you put this miniaturized patch on the high dielectric, let's say 10, with the height, let's say in this case about 0.06 wavelength. It still is narrow, but it's thicker than thin substrate. You see bifurcation and radiation pattern because the surface wave and space wave, they interfere and bifurcate. So one of the areas that you can use this metamaterial, you put them on these band gap structures, which are now holes properly created in this material in order to prevent propagation of surface waves. And it enhances your bandwidth and also overcomes that bifurcation. This is just an example that how potentially this metamaterial may be used to synthesize characteristics of some more miniaturized antennas. So if I jump over this one, then we are done. I just want to make one or two concluding remarks and hopefully bring it to some final. Okay, so what we've done today as a reference, we believe strongly that our antenna laboratory in cooperation with other institutions should be able to advance miniaturized antenna design concepts and development for modern communication applications. We also believe that we thank you for participation in this forum, and we look forward to collaborating with you. So with that, I want to finish with my last statement here, where I started, and that's the focus of a lot of research. It says, if at first an idea does not sound absurd, then there is no hope for it. And that's the way we typically struggle with our people who are trying to support us and give us research money and so forth. They always think our ideas we have are absurd. But I say, well, if Einstein says that, okay, you better don't support me. All right? Thank you very much for your attention. I'll be happy to entertain if there are any questions. And have a nice day for the rest of the day. Thank you very much. Any questions from the audience?
I have several questions, but I'll keep it to one or two.
Sure, please.
Number one, that you talked about 4x4 MIMO in a laptop environment. Now, as for the LTE and carrier aggregation and all those, the capacity of the network, they're trying to increase more and more. So if you look at like LTE release 11 to 12, they're going for 4x4 MIMO, 2x2 MIMO to 4x4. So my question is more related to the smartphones.
Sure.
Now, your antennas that you showed, you will be using the ground plane of the chassis or whatever.
Typically, yes.
So how will be the correlation coefficient? Because isolation is a very big parameter for MIMO antennas. So how do you think that can be integrated? If you can give some.
Yeah, I guess the question was a very important question on the MIMO deployment on different devices. Some devices are easier, some devices might be difficult. The first question is that the notion of 4x4. I think people have done a lot of communication evaluation, and it appears to be 4x4, you get the most you can get out of MIMO. You can go more, 5x5, 6x6, but 4x4 looks to be bring it to some kind of threshold that may not pay off. You go so much beyond that, at least with existing scenarios. Now, the second question of deploying a MIMO on the handset, actually we are looking into this right now, and indeed there is not much room. So therefore, you have to do more miniaturization, but at the same time, you have to worry about the correlation among these independents. And so that rho factor is very critical to see how effective these units work as a MIMO. And not only that, the research has shown that when you have multiple antennas on the cell phone, you also have to revisit this notion of the specific absorption rate and all that. It's not the individual antenna contributes, it collectively contributes if they're all active and so forth. So I guess what I've seen that looks to be people are suggesting that 2x2, they might getting some good results, but when you look at the detailed numbers in terms of correlation number, it's not yet as well accepted. So I'll be very interested, the future speakers in this forum, they probably are referring to some, maybe yourself also, to some MIMO consideration for small units. So the key is that you have to have them uncorrelated. That's very critical. And also you have to worry about the collective influence of your specific absorption rate. So there are a bunch of features that makes it more unique for the cell phone compared to bigger devices. Yeah, thank you very much. If there are any other questions, I'll be happy to. Oh, yes, please. Yes, I think time has changed. When we started, we were probably one of the first group internationally to look at the SAR. So we developed our own codes, and that's the one that came on the cover page of Proceedings of the IEEE. And we use fine difference time domain, rather crude model of the human, as you saw when even they put it on the cover page. It was a yeast cell, a little bit bigger cell. It was not the 1 millimeter model of the human. But nowadays, students don't want to develop new codes, so they all go and use some of the vendors' codes. It could be CST, HFSS, and so forth. So we evaluate them, either comparatively among the codes or with the codes that we have developed. Now, but of course, you know, ultimately in the industry, they don't rely on this competition. These are a good feedback. But nowadays, every cell phone, because I was in China, they gave me a tour of some of these places they build this cell phone. They have to go through a unit that they use this DAISY measurement apparatus that they actually try to measure. But of course, you are not allowed to measure in the presence of the human because you cannot drill into the human's head. So they use these mannequins, which supposedly they represent very similar material characteristics, predominantly, I would say, water or salt water and things like that, to do evaluations. So that's where we are. We believe in you can compute them reasonably pretty accurate. There's a lot of correlation between simulation and those class of measurements. But ultimately, we have to wait in another 30, 40 years when there's a lot of usage to see what the ultimate paradigm is in terms of health consideration. But I'll be happy to entertain, to follow up the discussion during the break. Yes, please.
In the cell phone industry, I think when they measure the antenna performance, they usually use so-called TIS and TRP. Yes. So because that will actually see how the antenna actually, how well it is integrated with the electronics. So have you, why not the antenna? Seems to me all the paper I saw doesn't gear towards that direction.
Yeah,
it's just
yes.
S11,
no,
S22.
I think it's a very good question. I gave that in a broader picture, but there are specifics. Yeah, exactly what you said. We actually had the paper on this when we look at the antennas, not just for both this communication, but also for GPS. So when you have this combination of antennas, you also have to be more careful. And the parameters that you refer to, yeah, indeed, we actually do those computation, or at least the assessment of that parameter as a signature of goodness. But I didn't go through details. Definitely true, yes. Oh, yes, please.
Great number of antennas. I like all the stuff that I saw. It's very nice. As far as miniaturization, are you looking at non-Foster circuits, anything along those lines? I'm just hoping I was paying attention because I don't remember hearing it. So.
Yes, I guess you know these areas are evolving. When we brought this notion of metamaterial into the game, other avenues were looked at. In particular, this non-Foster circuits that people are looking in terms of the matching part and so forth. We are directly not in our group looking at these non-Foster type designs, but I know places like I'm pretty sure HRL or many other organizations are looking at. One element yet to be appreciated, and maybe the research is going on, is the bandwidth properties and stability. So still there is a debate is going on if these circuits really have a good stability. if you look at the Nike's stability or whatever paradigm stability you're looking for performance evaluation. It has a potential future, no question, because at least researchers are still engaged, but how well it would really goes back to the industry utilization is something that yet to be looked into. That is correct, yes. Exactly.
You are bringing in a lot of nonlinearity into that, not just the stability. So I see there are lots of questions to be answered. I don't know if you can.
No, I do agree. That's why I wanted to get
Yes, indeed, indeed.
Research going on, but
No, exactly. I think people who have done research in this area, this nonlinearity in practice, as we know from classical control system, brings some chaos. And whenever chaos occurs, then you lose the stability and all that. But people are looking at that. So hopefully, if you go back to Einstein's, it is absurd, but maybe we are going to prove it may not. But
these are not just diodes or devices.
yes, of course, of course, of course. And ultimately for the user, the price is important. For what price you can do something for me. That is correct, yes.
So I hate to interrupt the
No,
great
please, I'll be
discussion, but
outside.
I think we should
Yes.
time for a break. Before that, I wanted to thank you, Professor, for your very nice talk and roller coaster ride through the electromagnetic world and the antennas. Thank you very much. Let's thank the speaker again. And